Oh well. In any case, I want to start as usual by reviewing a couple of things we saw before. So, we solved two important problems in theoretical physics. One that you knew the answer very well, the harmonic oscillator, and one which was the Heisenberg spin chain. And the Heisenberg spin chain was the last one we saw. We said, let's take an Hamiltonian. I put this minus sign behind the Hamiltonian because I want it to be ferromagnetic. So I want that when all the spins are aligned, this is the state of lowest energy, and whenever they are anti-aligned, this increases the energy, hence the minus sign. So we put that minus sign just so that our vacuum is everyone all spins up. And then I start with all spins up, and I start flipping one spin, and that's one magnet, flip two spins, that's two magnets, and these magnets move, and they scatter. And at the end, their dynamics is encapsulated by these so-called beta equations that tell you that if you take a magnet, carry it around, the total phase is 1. U is the rapidity of the magnet. It's a way of parameterizing its momentum. So that factor there is just exponential of the momentum of the magnet. So this was just definition of e to the I, the momentum of the magnet, as parameterized by this variable uj, while this is the energy of a magnet, epsilon of uj. And if you know the energy and the momentum, which you find by solving beta equations, you get the spectrum of the theory, which is bigger, where the energy is bigger than not putting anything, and this being bigger is the statement that we start with a vacuum, which is the ferromagnetic, and then we increase the energy. And we can now do many, many things, and we will do many, many things, such as considering many limits of these equations, putting a few excitations, many excitations. We can even put L over 2 excitations, which would be going to this antiferromagnetic vacuum, where we put half of the spins, we put as many magnets as half of the spin chain, such that we will really go very, very far away and very, very excited. We will do a ton of things that we can indeed do. Then we have the spectrum of the harmonic oscillator, which I wanted to write it in the following way. I want to say that the energy is 1/2 plus n, and write me like the n as a sum of the energies of each of the quanta. I want to say that this 1 is just the energy of the quanta xk. It's just a simple dependence, just a constant. It just doesn't depend on xk. It's a simple model. But as each quanta that I add adds an energy 1. And I could still solve some kind of bit equations. It would be a bit ridiculous to do it because the energy doesn't depend on this xj. But if I want, say, the wave function, if I want to know more information than just the spectrum, then I better also find the zeros of my wave function. And there was even some nice classical limit where these poles condense into a cut, and I could understand that this was related to a classical limit when I have many, many poles condensing into a cut. Okay? We will see, for example, perhaps I can do part of it now, given that today we have lots of time. We will even see that these equations here, these bit equations, are even more similar to these equations than you might think. And there are limits of these equations where they are very much of exactly the same form as the ones that we saw here. And for example, if you follow your nose and try to see what could be a good classical limit of these equations, you will end up on the spot with something very, very close to these equations. But let's postpone that a little bit, because let's first aim at covering what we need so that we can solve tomorrow's tutorial. But a good question you can ask here is, besides all these interesting limits that we will find out, we can ask, does there exist a semi-classical limit here? Okay, on this spin chain. And let me anticipate that the answer is yes. What's the physics of this semi-classical limit? It will be a limit where you have a very long spin chain and very long wavelength excitations that will become described by a field. So this would be the limit where you consider that you have a spin that's pointing up, and then it varies very slowly as you go along the chain. So you see that if you focus on a piece of chain, it looks locally like ferromagnetic vacuum, but it's varying very slowly. You can imagine introducing some sort of coherent states that change the direction slowly, and considering some limit of your spin chain where the spin chain is where the relevant degrees of freedom are not these well-localized magnets that are moving, but rather some very long wavelength excitations that move very, very slowly. And indeed, those will correspond to a classical limit, where in that limit the equations resemble strikingly to this one, and if we take many excitations, we will again get some cuts, and we will make contact with some well-known classical integrability stuff. Yes?
In what you were just saying, what is it that varies slowly as you move along the chain? You're saying, is it like the probability of measuring a spin-up? Or?
Yeah. Okay. Very good. We will study that in great detail on Tuesday, probably. So I will. So the answer is yes, and we will see in more detail how it works. Okay, very good. So there are a ton of different limits we can take. Many roots, as I said, small number of roots, large volume, not large volume, and so on. But before, let's try to get some intuition about this equation, and let's use again our physical way of thinking about this equation. This equation is too hard, and it becomes very easy if we take a logarithm of this equation. So let me tell you why. Suppose we take the logarithm of this equation, and let me write it in the following form. I'll just take the log, and divide by I. L over I times log, what variable am I using? Uj. Uj plus I over 2. Over Uj minus I over 2. Plus sum over k not equal to j of minus 1 over I times log of Uj minus Uk plus I over Uj minus Uk minus I. So I did not do a typo. I just put a minus 1 instead of flipping these two signs, okay? If you take the log, normally you would write the opposite sign. I put the minus 1 outside. And what is this equal to? Zero is one of the answers. Another answer. What else could it be other than 0? Sorry? 2 pi n. This, for each j, could a priori be 2 pi nj. Okay? Where nj is an integer. Okay? So when x equal y, log x equal log y plus 2 pi n. Okay, this makes total sense because if you remember, these equations, for example, when you have e to the I PL equal 1, of course, this does not imply that P equal to 0, but it implies that P equal to 2 pi n over L. Okay? So this is the same story, except that, as we said, it's a slight generalization, where now we don't have just momentum times length equal to 1. We get momentum, but we also get a small phase shift. Okay? So these guys here are called the mode numbers. And the claim is that if you tell me what are the mode numbers, the solution to this equation is unique. In other words, while there are many solutions to these polynomial equations in that form, and it's very hard to count them and to see what they are, the claim is that once you take this log, each choice of mode numbers gives one solution to those equations. So you can parameterize, you can label the solutions to these equations by telling me which integers do you choose. You can choose 0, you can choose 1, you can choose 2, you can choose whatever you want. Okay? Very good. Now, let's try to see a little bit why this is indeed very natural. Because what are we going to do? You see, first of all, I want to make a comment that these equations now look a bit more similar to these equations already. Right? And how did we think of these equations? We said, let's think of these equations as some kind of electrostatic equilibrium position, where I have some external force and then some interaction force, and I see where particles want to go. So let's do the same thing here. Let's think of this. Let's think of this L over I times log of U plus I over 2 over U minus I over 2. Let's put the integer as well, minus 2 pi n. Let's call this some external force acting on position U. It will depend on n. For different particles, they can have a different external force depending on the n that they have. But let's take one of them with one particular mode number, and let's think of this external force. So what is this function here? This function here is very similar actually to the function 1 over x. If U is very large, at U large it behaves exactly like 1 over x. So it's not different from the function that we considered before. This interaction force was 1 over x minus xj minus xk there. This is also behaving like that, except that when u is equal to 0, you get log of -1, which is I pi, you divide by I, so you get pi. So you get kind of a regularized 1 over x instead of blowing up. So this would be 1 over x. And this is kind of truncated here. It goes up to pi. And here starts at minus pi and goes here. So this is the plot of this function of one branch of this function. Of course, I can say that I choose another branch of the logarithm that differs by this one by 2 pi, but that's just redefining the mode numbers. So I choose one branch of the log once and for all, and then different mode numbers give me different solutions. If I keep changing the branch, then I'm overcounting. I mean, because, okay, I fix the branch once, and then I change the mode numbers. Okay? So this is this function. So if you plot, again, the force, what does this function do? Well, if particles are here, they are repelled. This is positive here, right? If particles are here, they are repelled back. If they are further away, they are repelled, but with a smaller arrow. If they are further away, they are repelled with a smaller arrow. And you can see in the imaginary direction, you can see that it's also like before. And this would be the vector field of this function. Okay? So good. So if you put this just a free particle here, what does this particle want to do? You put it here and it just goes to the right indefinitely. But you are not just putting the particle here, you are putting the particle, letting it roll, but then you are putting a constant electric field, a constant force that pushes it against where it wants to go. Okay? So what you have is you have L times this log. That function starts at L pi and goes down. And there is a value where it intersects 2 pi n. And this is the equilibrium position where particles want to go. So this is U equilibrium. Okay? So if I ignore this S matrix, for each mode number, they will go to different equilibrium positions. Okay? So ignoring the S matrix, what would happen in the complex plane is that I would have a bunch of particles here, a bunch of particles. I'm drawing them as if they are on the same position. So I would have a bunch of particles here, a bunch of particles here, where this is for all with the same mode number n1. These guys would have a different mode number n2, etc. Okay, so I take 10 particles with mode number 3, 10 particles with mode number 5, and they go to different equilibrium positions. One go here, the other one, this would be 2 pi n1, this is 2 pi n2. So this would be, if this is the origin, n1 bigger than n2. Okay, the bigger n1 is, the closest to the origin they want to go. Okay? And we cannot choose any n1, there is a bound, we cannot choose n1s bigger than L. We have to choose n1s between some L and some minus L. Okay, so we either put them on the right or put them on the left, but they are bounded. Okay, which is fine because we want a finite number of solutions, of course. And there should be finitely many. In fact, if we count the number of solutions, we should get 2 to the L solutions in total. So it better be that these mode numbers cannot be whatever they want. Like here, this mode number here, n, takes value 0, 1, up to L minus 1. If you continue, you are overcounting, then it's not new solution. If you take there n equal L is the same as n equals 0. Okay? So this is the picture ignoring the S matrix. Now let's put the S matrix. What happens when we put the S matrix? Well, now we have to consider the interaction force. So now we have some interaction force, which is minus 1 over I log of U plus I over U minus I. With this minus sign that I said was not a typo, this minus 1 here. So what does that force do? Well, it does the same as in this figure, but with the arrows reversed. Because of the sign. So what does this force want to do? It wants to attract particles and wants to push them apart in the imaginary direction. So this force, you put all this clump of particles and it wants to push them and spread them out in the imaginary direction. Is it clear? Because now, you see, it will pull out in the imaginary direction. So what do we conclude? We conclude that in the complex plane, basically two things can happen. For example, if I put particles in two mode numbers, what will happen is that they will go to some equilibrium position and then they will open up and draw some kind of umbrella shape. And this will be for N1. And then there will be another umbrella for N2. Etc. Okay? This would be the picture for most particles with same mode number. That is, the different mode numbers, the number of different mode numbers is much smaller than the number of particles. We have like 200 particles, but like 3 mode numbers. Then we have 3 umbrellas. Okay? There is another possibility, very different, where we consider most particles to have a different mode number. Particle 1 with mode number N1, particle 2 with N2, particle 3 with N3. Perhaps one particle we consider the 3 particles with the same mode number. But otherwise, we could also consider a case where most UJs have different mode number Nj. Then each of them will go to a different equilibrium position. Then the configuration will be mostly real. Okay? So we have at least two sets of solutions. One, we can have here one guy isolated, for example. One where it is mostly about complex solutions, mostly complex. And one where we have mostly real. You can imagine just a solution where all particles take different mode numbers, then they all go to some real positions, and we could ask what's the physics of the solution where they are all real, what's the physics of having just 2 of these umbrellas, and so on. Okay? You see, I mean, I want to emphasize again how powerful this electrostatic equilibrium picture is. Imagine you want to look at the original polynomial and ask someone, where are the zeros of this polynomial equation? And can you imagine without this picture saying, oh, they will form some umbrellas and so on, and you can even study the force and you can see that they are bent like this and so on, just thinking a little bit about some arrows. It's a very, very powerful way of thinking. For example, suppose I had a typo and I flipped the sign plus I and the minus I, right? In the S matrix. It was just a typo. Then the arrows would not be reversed. I would immediately conclude that there are no complex solutions because now the particles are repelled horizontally and attracted vertically. And I would immediately say, now I have a bunch of disjoint cuts, but they are all real. See? So just by looking at the forces and thinking a bit about this force, I can immediately say they are real, they are complex, they bend like this, they bend like that, they stretch like this, and so on and so forth. I find it really cute that we can do this. Okay? And there's some physics involved, because having complex solutions or not having complex solutions, as we will see, it's something physical and important. So let's explore a bit. Let's ask a couple of questions about these solutions. The most important of them being, what's the physics of these complex solutions? Okay? What is the physical meaning? We have a spin chain, we put a bunch of particles, and now we are finding these complex solutions. If you see that putting a U that is complex will mean putting a momentum that is complex. Okay? So let's see what is the physical meaning of this. Okay? So there are several questions we want to ask now. We want to ask, what is the physical meaning of these umbrellas, of these arcs? So let's, a couple of questions. So what is the physical meaning of these arcs? And then we want to ask how bent are they? Are they very bent? Are they almost straight? Etc. And we will see that that it does matter, and we will see why and what's the meaning of this statement. That's kind of a more mathematical question. And we want to ask, for example, is there a condensation of roots into cuts? Because it definitely sounds like from the picture I'm drawing. Is that the classical limit? You see? Now it looks like, okay, these guys will condense into some cut, another cut. Can it be that we will start seeing these cuts emerge? And could this be our classical limit that we are after? Okay? Good. So let's start by the second one, because knowing more details about these strings will help us understand their meaning better. So now there are several limits we can take. And we will start, let's take L huge and N order 1. So we take like 10 particles and L equal 1 million. Okay. And we go and look for complex solutions of these equations to try to see what happens to them. So now let's consider that there is U of order 1. And I want to take mode number to be of order 1. Okay. What would be the other alternative? They could be either of order 1 or of order L, right? They go between minus L and L, roughly. So they can be either of order 1 or of order L. Being of order 1 will imply that the corresponding U is of order 1. And had we chosen instead Nj to be of order L, it would imply that the Uj would be of order L. Okay? And that should be kind of clear, because what is this equilibrium position? This equilibrium position is roughly what? You equate 1 over x with this, so it's roughly 2 pi n equal L over U. Approximately equal, because I mean, the function is not exactly 1 over x, it's this log, but if you want to estimate more or less, this is it. So if n is of order L, U is of order 1, and if n is of order 1, U is of order L. So I said it wrong. Funny, why? L, n of order L, U of order 1. N of order 1, U of order L. Okay. So we want n of order L. Okay. In fact, I'm not going to use the logarithm form of the equations. The logarithm form of the equation today was just to get an intuition where the roots go. I'm going to use the product form of the equations, which has this nice physical meaning of particles going around. And what I'm going to do is look for solutions where the roots are of order 1 and solve that polynomial equation. So that's why this was not very crucial to say what the mode numbers are. Okay? Any question? No? So let U1 be the root with the biggest imaginary part. Okay. So it has some imaginary part, so u1 is equal to u plus I eta, where this eta is positive, and it's the biggest imaginary part of all the roots. Then, what happens if you focus on the equation for u1 is that u1 plus I over 2 over u1 minus I over 2 to the L. If u1 has a positive imaginary part, this is huge. Right? So this blows up. If u1 has a positive imaginary part, this quantity is very big. Is it clear? Because the absolute value of the part above is bigger than the absolute value of the term downstairs. Okay? Is it clear? Again, if something is not clear, tell me, I will explain. So this term blows up. So what happens then if you look at the equations? That term blows up, so you need a term in the product of S matrices to go to 0. Okay? So we need a root u2 such that u1 minus u2 minus I over u1 minus u2 plus I goes to 0, such that the product of the two would be finite and we have any chance of solving the equations. Which means that we need a u2 to be equal to u1 minus I. Okay? Approximately equal. Very close to u1 minus I. So what we did now, we have two options. One option is, what we found is that if this is u1, we need a u2 to be separated by a distance I. Okay? And it's kind of fun, you see. Right away you can imagine, if the S matrix had the wrong sign here, by reduction, I would immediately reach a contradiction, because I would say this explodes, and then I need a u2, where the sign is different, so I need a u2 to be u1 plus I. But u1, by assumption, had the biggest imaginary part. So that's impossible. So there can be no complex solutions. You see? So it's good. But now it can. u2 is u1 plus I. Now, there are two options. Imaginary part of u2 is still bigger than 0, or imaginary part of u2 is smaller than 0. If it's still bigger than 0, then you show that there must exist a u3 such that u3 is equal to u2 minus I. Because then when you go to the equation for u2, this term will explode, and you need a u3 to cancel it to 0. And in fact, it's even more dangerous than that, because this term explodes, and the interaction of u2 with u1, which is the inverse of this, now also explodes, so you get infinity square. So the role of u3 is to cancel this infinity square, so they need to be very, very close to y. Okay? So let me write it by word. So this here, in that case, u2 plus I over 2 over u2 minus I over 2 to the L will go to infinity. And another term in the same equation, which is u2 minus u1 minus I over u2 minus u1 plus I, also goes to infinity. So we really need a term like this that needs to cancel two infinities. So the conclusion at the end of the day is the following. The conclusion is that in this limit, where the roots are of order 1, these strings, these umbrellas, are not bent at all. In fact, these guys are separated by 1. They are exactly I, this distance, with exponential precision. Exponential comes because it's the exponential term that is driving this. Okay? And if the mistake here is exponential, the mistake here, the deviation from I here, it's even a smaller exponential. Okay? So it's a very, very bent, very, very straight string. Maybe at the end is slightly bent, but in the middle is really super exponentially precise, right? Okay? So it's very, and here it's even more straight. So in general, we can have, therefore, these objects which we call n strings. They are strings of beta roots. In this case, we have n equals to 4. And we could have strings of size 2, strings of size 1, which is no string at all, strings of size 10, whatever we want. Okay? Yeah. Now, good. So in general, what we will have is we will thus have a bunch of strings. We can have a string of size 3, a 3 string, then a 2 string, etc. We can have now a state of many strings and so on. Okay? With exponential precision. Now, just to make a point that it is important, it was important that U is of order 1, which we know, even though we did not use, but we know that this corresponds to n of order L. Right? Why? If U were of order L, then U plus I over 2 over U minus I over 2 to the L, this is definition of exponential. It is just exponential of I L over U, and this is finite, right? If U is of order L. So if the roots are large, if U is very large, you cannot just say that if it has a positive imaginary part, it explodes and so on. No, it just goes to some finite value. And then what you expect in this case is that the roots start to bend. So there is a case, if the roots are of order L, where they are not so straight as before, and they start bending. Okay? That's the picture. Okay, now that we understood the math well, we can go and ask about the physics. So what's the physics of these strings? What is the meaning of a string? So does someone want to guess? How would you, if you don't want to guess, let me just ask you, how would you go about trying to find out what the physical meaning of it is? So you don't know the answer and you want to figure it out. What should you do? What could you do to try to answer this question? What are these strings? What's their physical meaning? I'd say that's that's all a bit overkilling, yeah. You can do something a bit simpler. This is not a semi-classical limit. You see, this magnon is a quantum excitation. It's really a quanta that is moving in our spin chain. There's no particular sense in which this object is classical. It's really quantum. And if we have a string of 2, it's still going to be a quantum object. It's not ideal to do semi-classics. We will lose lots of the physics. This is really a quantum thing. We could look at the spectrum. That's a good point. Yeah, indeed, that's what you are going to do tomorrow morning, one of the things. That's a good point. Let's do something which is not there. So similar. Let's take a 2 string. So let's consider a 2 string, which means that we have basically U plus I over 2 for U1 and U2 equal U minus I over 2. Okay? So let's take this 2 string and let's ask what happens to our wave function. Okay, what happens to our wave function? Well, our wave function, remember, it has U1 plus I over 2, but U1 is U plus I over 2. To the power n1. Same thing with the power n2 for n2. plus this matrix, but this matrix is what? U1 minus U2 minus I over U2 minus U1 plus I times some factors of momentum. But I'm not going to bother writing them down because we see that this term is equal to 0. We are at the 0 of the S matrix. In fact, that's what we imposed. We said we need to go to a 0 of the S matrix such that things work. So it means that we killed one of the terms of our S matrix. We went to the 0 of the S matrix. Or if we have normalized the S matrix different, to the pole of the S matrix. And these zeros of poles of S matrices, precisely because of this reason, because they kill one of the ways, have an important meaning. They are what are called bound states. So what we did is we created a bound state. We killed one and we created a bound state. And let's see it very clearly, because this is nothing but the following. Let me write and you see if you agree. This is just U plus I over U minus I to the power n2 minus n1 times U square over U square plus 1 to the power n2 minus n1. So let me see. So U plus I appears with power U to yeah. Sorry? The first exponent should be plus, of course, yeah. Yeah. Good. Do you agree? You see? Yeah, it's clear? Let's see. U appears to the power n2 minus n1. Is it correct? Let's see. U appears here, upstairs to the power n2, and here to the power n2 minus n1. Indeed. So this U squared to this power is good. Then let's look at U plus I. U plus I appears with n2 plus n1 over 2, but also here. Downstairs I can write this as U plus I, U minus I. So then 2 doubles, and then 1 cancels. No. Then 2 is downstairs. So then 2 cancels and then 1 doubles. And indeed, then 1 appears here and there's no n2 with plus I. So that's correct. Okay? And now this has a very clear meaning. So what do we have here? Here we have exponent. This part is just a phase. So this is just equal to e to the I p. Let's put an index 2 to indicate it's a 2 string. Of U times the center of mass position, n1 plus n2 over 2, okay, which is just n of the center of mass, times a factor that is between 0 and 1, so it's smaller than 1, and remember that n2 is bigger than n1. So this distance is positive, so this is a factor that decays as you separate n2 and n1. So times e to the minus some imaginary part, let's call it eta, times the distance n2 minus n1. So this is a very clear wave function. It describes a bunch of spins up. And then there are 2 spins down that want to be close to each other. And that move with some momentum. There is also a possibility that I put n2 minus n1 not to be 1, but to be 2. But that's more suppressed by this. So they are not exactly close to each other. They are a bit delocalized. They start to have some size. They are not forced to be. They don't need to be exactly close to each other. But they want to be close to each other. Okay? If you put a wave function where they are close or where they are separated by 1, the second one is more suppressed by another e to the minus eta. Okay? And you have this guy, and it moves with some momentum p2 of u. Okay? So then, now the physical meaning is very clear. This 3 string here will, of course, describe a bunch of spins up, and then a bound state of 3 spins that wants to move close to each other on the spin chain. And then it meets a 2 string where you have 2 guys that like to move close to each other, and so on and so forth. So what these strings are, they are blocks of ferromagnetic state. So we have a big ferromagnetic state, and then we have blocks of ferromagnetic, like trucks that are moving on your spin chain. So you have these small particles, small spin flips, but they can also form blocks. And this is very reasonable, because you see that if you have a big block, the internal energy of the block is 0, because if you now measure the energy inside, it's ferromagnetic, so it's locally very good, energetically. So all that costs to make a block is the boundary energy of the block. So in other words, as soon as you have spins, they like to be close to each other. Why do they like to be close to each other? Because if they are close to each other, they generate a ferromagnetic vacuum, and the vacuum is energetically favorable. So when you have spins, you can immediately think that they attract. So they better form bound states. So this bound states is natural. As soon as I told you that I put this sign for the Hamiltonian, you could have said, well, but then your excitations will move, but they should be able to stick to each other, because they will want to form these blocks. Because a block of spins up is very good. It costs no energy except at the boundary of the block. That's precisely what we find. We find that this wave function is exactly described like this. Okay? Is it clear? In your tutorial, you will now consider what is the wave function for 2 strings. And it's kind of a nice example that illustrates these points about the S matrix of these objects and the fact that the S matrix you measure when the objects are separated. So what will you do if you have now 2 strings? Well, you start not with 2 particles, but with 4 particles now. And put 2 guys with momenta u plus I over 2, u minus I over 2, and 2 guys with v plus I over 2, v minus I over 2. Okay? And then you will first see that many terms of the wave function are 0. And furthermore, you will see 2 things. You'll see that when particles are very well separated, only 2 terms survive, which is the incoming string and the outgoing string. And then you read the relative coefficient is the scattering of the strings by one scattering through the other. But when the 2 strings are close, because they have some finite size effect, because these strings have these tails, when they are close, you will get a mess. We did not get a mess when we were describing a single excitation, but you will get kind of a mess when the 2 strings are close in this case. Which is what we expect, because these strings, they are not well-localized objects exactly close together, but some Gaussians that are moving and move by each other and scatter by. So I think it's a very nice exercise to understand a bit more the physics of this S matrix and locality and so on. And this is the main exercise for tomorrow. But another thing you could also do, and it's also in tomorrow's exercise, is to take this string, and out of this string, compute the momentum of the string, we just did, and compute the energy of the string. Well, what is the energy? The energy is just the energy of a U1 plus the energy of a U2. Okay? So you compute and you get some expression. And then from this 2 you compute what is the energy as function of P by solving this parametric equation. And you can compare this as what's your name, sorry? Ilan. As Ilan was proposing, you can compare this with what is the energy of 2 fundamental particles with P1 and P2, where the sum of P1 plus P2 is P. Okay? And you should find that this one is smaller because it's a bound state. And that's indeed another thing that you will find in tomorrow's exercise, reinforcing this idea of bound state and of interaction picture. Good. Good. So now, we'll consider now a slightly I want to consider now a slightly different limit, which I find quite illuminating, and it's much less well known. Okay. Now, so again, to summarize, so what we have seen is that in general we have these n strings like that. So this configuration, this kind of configurations where we have all spins up and then spins down, they are good, as we said, because here we have locally energy equal to 0. Here we have locally energy equal to 0. So all the energy cost is in these barriers. So you see that it doesn't cost much to increase the size of these trucks, and that's why these objects are very favorable. So energy is concentrated here at the kink, in the so-called kink region. Now, you could imagine trying to do something that has even less energy than this configuration, which would be removing the kink altogether. We could do even better. Okay. By starting with all spins up, and then varying the spin very slowly, such that mid, who I'm always close to the blackboard, I don't even see that the spin is state. But soon, I'll catch this in a minute. Okay. So if it varies very, very slowly, locally, whenever I zoom, it also looks locally like ferromagnetic vacuum. So if I consider some wavelengths which are of order L, some spin waves that move with some very long wavelength, I could imagine generating energy which are very, very slow. It costs almost no energy if I bend the spin very, very slowly. Is it clear? So what could be this limit? So let's try to identify what could be this limit. So wavelength of order L, it implies that we want momentum of order 1 over L, right? Momentum, very small momentum. Momentum of order 1 over L. What would be momentum of order 1 over L? Well, momentum of order 1 over L means that U needs to be of order L, right? So this is equivalent to say that U is of order L. Okay? So when U is of order L, and let's say that the number of excitations is also of order L, so we put many, many excitations, then our energy, which is the sum of 1 over U squared plus 1/4, would be of order 1 over L. Okay? It's a sum of L terms, each of them 1 over L squared suppressed, so it gives of order L. So there are indeed this family of states where I have many, many excitations, but they have such low momenta that the energy is really very close to the ferromagnetic. It's a very low-lying energy sector where the energies are very, very close to the ferromagnetic vacuum. And in this case, we will see that it becomes reasonable to describe these spins by a slowly varying field. Which we will see can be described by a vector n that changes along the spin chain. So to describe this field is very convenient to introduce so-called coherent states. So these are coherent states n with an expectation value of the spin generator on the state to be the vector n. Okay, over 2 because spin 1/2. So these are states where the expectation value of the spin is n. They are like coherent states, like we use them for harmonic oscillator. And I just want to introduce them because in the homework for the weekend, what you will do is play a bit with these coherent states, developing the kind of techniques that we will need when we will be studying this physical limit in detail next week. Okay? But instead of going directly from this limit to this limit, there is an intermediate limit where we start seeing a bit the physics of what's going on, and that's the limit I want to consider, which is kind of something in between, where we will consider where we will consider that we are going to consider strings of order L, but not many excitations, just a few excitations, such that this height here is not of order L, it will be smaller. Okay? So let's see what this gives. And it will become very clear why I find this limit interesting. And it's actually a very simple limit to consider. I don't want to erase. Okay, I'll go here. Can I write here? So let's say that uj is equal to 2 pi L over nj, because that's the equilibrium position. That's where they want to go when L is large, right? This is what we said above. Plus delta uj. Right? Let's try. Okay? So again, what we will have, let's call this guy, let's call it xj. I don't want to carry a delta around. And we will see, I'm not going to assume, but I want to anticipate that we will see, so this will be self-consistent, that this xj is much bigger than 1, but it's much smaller than L. So it's reasonable to treat it as a perturbation. In fact, we will see that it's of order square root of L. Okay? So we can keep this in mind when we do approximations. But the point is that this U is very big. Okay? It's very large. Okay. And now we plug this, okay? We plug this into the equations and we start working it out. So for example, L over I times log of uj plus I over 2 over uj minus I over 2 minus 2 pi nj. Let's see what this term becomes. This term, if I write this for uj very large, this term is I over uj. Can someone expand this in Mathematica? It's a bit tough. For large U. Okay, I can do it. It's okay. So we get 1 plus I over 2U divided by 1 minus I over 2U. We want to expand log of this when U is very large. This is Is this correct? Can someone expand this, please? Large U? Series, blah, 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 large U? It's not. No, sorry. Of course, this is not correct. Okay. Okay. Let me jump to what the result is, because it's just expanding functions. Who cares about expanding functions? You can then expand it yourself and check that the fall. No, but that was U close to 0. I mean, what I was writing could not be correct. Yeah. Now I just want to take this, plug into the equations and expand, but let me tell you what the result is. Okay? So you just take this approximation, plug it into bit equations, and expand. And you see, I mean, okay, let me write it back again. L over I log of uj plus I over 2 over uj minus I over 2. This to leading order is approximately equal to L over uj, as we were saying, and as you checked, right? And this when I plug that approximation, is equal to 2 pi nj. Okay? So the leading order result just cancels out, and then I need to expand further to find what is the equation for xj. Okay? And when I expand further, I expand this further, and we get the following. We get xj times 4n square pi square over L, so that's just a constant, times xj, plus sum over k not equal to j of 1 over xj minus xk equal to 0. So I find this quite nice. So what are we seeing here? We are seeing that close to this cut, what we get are exactly the same equations that we were getting for the harmonic oscillator. Okay? So what we see is that what we have basically in this limit is that close to each of these cuts, it looks like I have an harmonic oscillator 1, another harmonic oscillator 2, and so on and so forth. Like I have a bunch of harmonic oscillators, each one with its own frequency. You see n enters there. This is for a given nj. So the guys with the same nj describe some of them. And you see that this equation is not exactly of the form I wrote there. The form I wrote there for the harmonic oscillator has a minus sign between the two terms. And this one has a plus sign. So what does it mean? Well, the same story. It means that they are complex instead of imaginary. In other words, if I write xj to equal to I zj, and I plug it there, then here I get I, here I get minus 1 over I, so I multiply by I flip the sign, and I go back to those equations. So basically, it means that to leading order, what I will have is that the roots will go here, and if I have just a few, here I will have solutions to Hermite polynomials. Okay? So what should be the physical meaning? What should we be observing as what should be the physical meaning of what we are doing? Well, what we expect is that when the U's are becoming very large, we should expect to get some kind of field theory, right? We said that when U is very large, we are describing long wavelengths, and we should be describing a field theory. Now, what is a field theory? What should be a field theory? A field theory, we have a bunch of fields, and we can mode decompose our fields with different frequencies. It will be like a vector that will go around our spin chain, and we decompose into the various modes of our vector, like modes of a string. And each mode of my field theory, I should then start quantizing it. But what is quantum field theory? Just a bunch of harmonic oscillators. Each mode is like one harmonic oscillator. That's exactly what we are seeing. We are seeing that our equations decouple into sectors. Each sector is like an harmonic oscillator. But then reality is more complicated than that. As soon as we start feeling it more and more and more and more, this picture where I just decouple the different harmonic oscillators here, they start coupling. Now it will be a bunch of coupled harmonic oscillators. Not decoupled anymore, but now the equations are more complicated, and we need to start coupling them and seeing the interactions between the different harmonic oscillators, and that's real field theory, and not just a bunch of decoupled harmonic oscillators. So this is a corner where our spin chain decouples into a bunch of independent harmonic oscillators. It should correspond in the field theory, and it does, to a limit where we are exciting, not much, some modes of the string, and we are exciting it so little that it is the field theory is still weakly coupled. We also see that indeed, in this equation, if you want to see how do these guys scale, you see indeed this x scales of order square root of L. Because if you scale x to be of order square root of L, you get 1 over square root of L. You get square root of L here, the square root of L cancels, and it's consistent. So everything becomes of order 1. So from this equation, you conclude that x scales of order square root of L. So there is this limit where you have a center of mass of order L that describes some long wavelength mode, and then you consider, you say that instead of exciting that mode, I start with just one quanta, I put several quanta on that mode, And putting those several quanta is just like an harmonic oscillator. Adding more quanta to one mode is very simple and obeys the same equations as for the harmonic oscillator. But that is totally intuitive. It makes perfect sense. When we start with the field theory, we focus around the given mode, and a quantum field theory is just a bunch of harmonic oscillators, one per mode. Okay? But more generally, now we can anticipate a little bit more generally what's going to happen. What's going to happen is that what this field theory will describe in the low energy limit is not a weakly coupled theory. It's a complicated theory that in general it's quite hard to solve. And what we have here with this solution of Pitt equations is a generalization of a Fourier decomposition, of a Fourier quantization of our model. And here is the picture. The final picture will be as follows. We will have our quanta, and there is here a bunch of excitations. And here is another cut with a bunch of excitations. And when you quantize a field, often phi, you write phi as a sum of some amplitude, right? Times exponential of I and sigma, and so on. Right? If the theory is weakly coupled and free. So the analog of this mode number is the mode number here. N1 for this guy, N2 for this guy. It tells you which mode numbers you are excited. The number of particles here, this N1 here, N1 excitations here, N2 excitations here, the analog here is what's the amplitude of the Fourier mode that you are exciting. How many do you put? Except that these are not all decoupled, like in string theory, where you just write your string decomposition as a bunch. You create stuff at each of the modes, and they are all decoupled. It's just free bosons. But instead, this umbrella interacts with this umbrella. These guys are bent because of this guy. In fact, the one that is more to the right, for example, bends like this because of the interaction with this guy. So these are not independent, but these are the closest analog we have to just an independent bunch of Fourier modes. Okay? So again, number of particles in a given cut corresponds to the amplitude of our quantum field. Mode number associated to the cut corresponds to the mode number of the associated field. Okay? So this would be, this we will see will be the picture that that we will see. So next time what we will see is start exploring this limit of very long strings, which now we know we start to get a grasp of the physical meaning. So again, what is it? So in the quantum regime, they are strings. They are very quantum objects. It's really like a particle. It's a bound state. The analogy is having a bound state that you scatter at LHC. Here you have a bound state moving in your spin chain. It's a particle. It's a quanta. It's very quantum. Now, if you start with these strings, which are very quantum, and you can make them more smooth by taking this limit where the wavelength varies slowly. So that means that instead of considering momenta of order 1, you start decreasing the momenta so that it becomes more and more delocalized. Then they become more semi-classical. The wavelength becomes much bigger. Now the center of mass of these strings is very big. And you start growing them. If you have just a few of them, if you start with U very large and start growing these strings, because they are very far away and you start growing them, they are all more or less independent. And they are just described by a bunch of independent harmonic oscillators, which are the different modes of my low energy field theory. As we start increasing them more and more, we are getting some complicated distribution of roots that are interacting with each other. This cut interacts with this cut, this umbrella interacts with this umbrella, and so on. What should this describe? It should describe an interacting quantum field theory, or the semi-classical limit of an interacting quantum field theory. And indeed, we will then take all these roots, take this limit where all these roots are so many that we can rather describe them in terms of cuts, and understand what's the physical meaning of these cuts, and how do we understand what's the underlying field theory, and how could we have gotten directly to this picture, starting now from the low energy dynamics of quantum spin chains, rather than going through the quantum version and then taking a particular classical limit. And this will teach us about how to semi-classically quantize integrable and sometimes non-integrable models. Okay? So that's the plan I understand that today's lecture perhaps was a bit hardcore, so please tell me if you have any questions, or if I should repeat some of the things I said now. Yes?
So what is the meaning of the banding? Because you can have just one string band, right? It's not just from the interaction.
Right. So you see that the string being totally straight means that it's a perfect bound state in the sense that you really killed all the terms. So the string being slightly bent means that the object starts losing its meaning as a particle that is moving as a single particle, and it's becoming something more delocalized. So I would say it's not unrelated to the statement of having long wavelength and so on. Yeah. More? Yeah, it's exactly that, actually. It's exactly that. Poles of S matrix are bound states, right? So when our physics is really localized at poles of S matrices, we are describing bound states, which are particles that move in a big spin chain and they are quanta and so on. Here, the physics is close to bound states. It's more like resonances. We are indeed not far away from the poles of this matrix, but it's more like an effective effect. I mean, it's important that these poles are there. Otherwise, the strings will not be complex to start with. They will be tilted, but we are not really going exactly to the poles. We are just exploring already some more effective description. Yes. Yeah, complex. So let me recall that the map between U and P is just that U plus I over 2 over U minus I over 2 equal to e to the IP. Or if you invert, U is 1/2 cotangent of P over 2. So U real is P real, U complex is P complex. Okay, you see? Now, you could write, you see that these variables, U, they have many, many advantages. One of the advantages is that they trivialize physics of bound states. You see? A bound state is just an object where U's are separated by I. You can ask, what does that condition translate in terms of P? It's something complicated. You see, it's 1/2 cotangent P1 is separated from 1/2 cotangent P2 by I. So these statements about what is the position of the bound state, what's the imaginary part of the momentum, right? At a bound state, we will have P1 equal P center of mass plus imaginary part, and P2 equal the same thing with minus. But to find the precise P center of mass and the precise eta is kind of complicated. It becomes trivial in terms of U. It is just U plus minus I over 2. So these rapidities U are just a useful parameterization of the momenta. And they are useful because they trivialize physics of bound states. Another way to trivialize is that the momentum, which is given by that, I can also write it as log of U plus I over 2 minus log of U minus I over 2. And the energy, I can write it as I over U plus I over 2 minus I over U minus I over 2. And why is this very useful to do? Because now you see that if I take my energy and my momentum and sum the energy and moment of stuff that is separated by I, there is telescoping and most terms cancel. And this leads right away, because it's like this. Now if I put not the momentum of one excitation, but the momentum of n excitations, all I do is put an n here. And now you can compute the energy as function of momenta for an n string. So this U is a very useful variable. It trivializes describing bound states. As you see, the poles are just separation by I. The energy is trivial to compute for a general string. And it removes all this trigonometric stuff, all these cotangents and so on, and makes all equations into algebraic equations. So I think there's no disadvantage for this use, but it takes a little bit getting used to. But I think all we have to keep in mind is we have to remind when we think physical is just U large is momentum small, and U small is momentum order 1. Provided you keep this in mind, the only thing that is a bit counterintuitive is that very low momentum is at infinity in the complex plane. But once you got used to U equal infinity being P equals 0, it is just a change of variables. There's nothing deep to the U plane. More?
How is it related to the spectral parameter?
To the spectral parameter U that we introduced before? It's the same. It's the same, but it's the same, but in a way that will take me more than 5 minutes to explain why. I mean, here they have a very different physical meaning. So let me say that it's not the same instead. It's not the same because the spectral parameter was something that we put to introduce the R matrix. We take derivative and we put to 0. So it's kind of an auxiliary stuff. We put and we remove. This, no, we put the particles and they give some energy. They are something physical and so on. But then you could ask, well, but when we were thinking of this R matrix and we were saying that we have a particle with momentum U, can I think of this? Is it more or less the analog of having one of these particles scattering with the other guys? And then yes, the answer would be yes. So there are connections, but they are subtle. A priori, it's not the same thing. Spectral parameter was an auxiliary parameter. We make sure our Young-Baxter's equation is satisfied, but at the end we put it to 0. These beta roots, no. Each set of beta roots gives one state of our quantum spin chain. And we just have to solve bit equations. More questions? I think tomorrow we will have a survey to fill, right? Every first week you have a survey. I would really ask you to please fill it in time, because it's kind of useful. I would like on Monday before the lecture to start to have the survey. I suspect many people will say this lecture was a bit too fast. And I want to make sure if there are stuff I have to review, if there are things I'm going too fast, if there are things I'm going too slowly. So I really ask you, please do fill in the survey tomorrow as soon as you get it. Okay, have a nice weekend.